Hey guys, welcome to Allotronics. In this video, we are talking about power amplifiers, nonlinearity and predistortion. Today we have a lot of simulations to understand how the nonlinearity of the power amplifier distorts the modulated signal. What is signal regrowth and why it happens for multitone modulations, and how a nonlinear model of the amplifier can be used, reducing the effects of the power amplifier nonlinearities and increasing efficiency. Take your coffee and come with me. You are watching Allotronics. Let's first understand the general concept of a power amplifier. The power amplifier is the last building block of a transmitter, is the last building block of a telecommunication system that needs to transmit a signal over the air, over a very long transmission channel. And what we expect from a linear power amplifier, from an ideal power amplifier. A linear power amplifier will only be generating in its output an equal copy of the signal present in its input. An equal copy, but enlarged with higher voltage and current profiles. And of course, this means with higher power available in the output. So the task of the power amplifier is to amplify the signal without changing the characteristics of the signal, without changing the waveform, without changing the envelope profile, and without changing the phase profile of the signal. But what happens in real amplifiers is that we have nonlinearities. Of course, we have nonlinearities in all subsystems of a transmission system, but this is especially a problem on the power amplifier. And we are going to understand after that this is also a trade-off between efficiency and linearity. And the problem of having nonlinearities in the power amplifier is that a nonlinear system distorts the signal. And what is distortion? Why distortion is a problem? Because distortion creates new components on the spectrum. I have a video talking about this here on the channel where we can see exactly how the distortion and the different distortion types generate new components in frequency, but we can easily see that this is a very big problem, because if we have distortion, if we have nonlinearities, the output of the power amplifier will not be an enlarged version of the input signal. It will be a different signal with a different phase profile, with a different envelope profile, and this means that we are transmitting a different signal. We are distorting, we are corrupting the information that we added to the signal in the modulation step. One problem we see here that's called signal regrowth. Look at this. We have this is the ideal output of the amplifier, but take a look that in the output of the nonlinear amplifier, we are generating new frequency content that is leaking to the other channels. This signal content here was generated by the nonlinear process inside the power amplifier, and now we are not only corrupting our modulation channel, we are also corrupting the adjacent channel. Take a look on this. We can see easily the distortion generated by an amplifier, and this is actually a common way of measuring the distortion when we apply two signals, two very clean signal sources to the input of the amplifier. So we have here two ideal oscillators generating two very clean signals, and we see that we have only two frequency components. Of course, this summing block here is a linear process. But when we excite the amplifier with this two-tone signal, we see that in the output of the amplifier, we have new frequency content. And all this new frequency content that appears in the output of the amplifier that were generated by the nonlinear process are called intermodulation products. And these tones are called intermodulation products because they fall inside the bandwidth, the operational bandwidth of the amplifier. It falls inside the modulation bandwidth. These new terms are corrupting the modulation. I made a simulation here so we can understand how the nonlinearity will shift the power from the fundamental tones to the harmonics and to the intermodulation products. So what I did here, guys, is to generate, I created here an arbitrary transfer function that is nonlinear. And we see here that with this arbitrary transfer function that we are using here as our amplifier model, we have the small signal region here in the middle where the amplifier is behaving linearly. We see that the slope here in the center is very linear, and here for very small signals the amplifier behaves as a linear gain block. As the input voltage of the amplifier increases, we see that we begin to saturate the amplifier, and as we try to excite the amplifier more and more, the output of the amplifier will not respond because we are saturating the amplifier, we are approaching the limits of the amplifier. And this region here is called large signal region, because for these regions here and here, we excite the amplifier with a so strong signal that it runs to its limits and the linear assumption is broken. So we have small signal region here in the middle of the transfer function and large signal region here on the sides when we approach the limits of the amplifier. And this large signal behavior comes from the power supply limitation. Of course, the amplifier cannot amplify the signal to infinity. It has a power supply limitation. It has the active device limitations, the maximum current, the maximum voltage. It has the topology limitation, the maximum output power for that topology, for that matching network that's being used in the power amplifier. If it's a class E, a class F, a class D, a class A, a class B amplifier. And we have also nonlinear components inside the active device, like junction capacitances and thermal effects that are changing the behavior of the amplifier in real time. All these effects in conjunction contribute to the limitations of the amplifier to this non-linear behavior in the extremes of the voltage excitation. So if we excite the amplifier with a very low signal, a very low amplitude signal, we will be working in the small signal regime here in the middle of the transfer function, and the amplifier will behave much like a linear system, amplifying the signal without generating new signal components, new spectrum. And we can see it here on the simulation. Take a look at these guys. Here we have a sweep of different amplitude excitations. We start with a very low amplitude signal exciting the amplifier in the small signal regime, and as we increase the amplitude of the excitation, we can see that the amplifier starts to clip, it starts to distort the signal. And if we take a look on the output spectrum, look at these guys. As the signal amplitude increases and the amplifier starts to distort, we see that the output power starts to be shifted to the harmonics and to the intermodulation tones when we test it here with 2-tone signal. So take a look at this. When the amplitude is very small, we almost don't have harmonic content, but as the signal clips, the power starts to be shifted to the second harmonic, third harmonic, fourth harmonic, fifth harmonic here. And the same occurs here for the intermodulation terms. Take a look, for very small amplitude signals, we don't have any intermodulation, but as it increases the amplitude, power starts to be shifted to the intermodulation terms. Look at this. So for a single tone, we can measure the nonlinearity as a total harmonic distortion, considering the energy on the harmonics. But this is not so useful for a telecommunication system because the harmonics are very distant from the operational bandwidth of the amplifier. All these harmonics can be easily filtered, but the problem is the intermodulation, as we see here, because the intermodulation will fall inside the operational bandwidth of the amplifier. Take a look at this. So imagine now that we don't have discrete tones, that we have a band of energy here. All these frequency components inside the bandwidth, all the energy that is contained in this bandwidth, this modulation bandwidth, will intermodulate and will distort the signal inside this bandwidth of modulation, distorting, corrupting the information we are trying to transmit. This leads to the problem of spectral regrowth. So take a look at this. Here you have a bandwidth of modulation, an information bandwidth, and we see that when we apply this signal here to the nonlinear transfer function, this transfer function here, we see that we have new components in the spectrum. We have components that are corrupting the information in the adjacent channels. So imagine that if we have another channel here transmitting in the side, we are placing energy inside the adjacent channel in the other side also. And we also have all the intermodulation terms that fall inside the modulation, corrupting or on information we are trying to transmit. And I'm trying to not go too mathematical here, but all the intermodulation terms that fall inside the modulation bandwidth are the odd intermodulation terms, and they come from the odd powers if we model the amplifier as a polynomial. So if we model the transfer function of the amplifier as a polynomial, all the intermodulation terms, like the third order intermodulation terms, these terms here, come from the third order term of the polynomial. The fifth order intermodulation terms that we saw on the simulation comes from the fifth order intermodulation term that goes here on the polynomial. So you may ask yourself why we are not using very linear amplifiers. Why we are not designing very linear amplifiers so we don't have all these problems that the nonlinearity generates. Well guys, actually we have a trade-off between linearity and efficiency. Take a look at this graph here. Here we can see two main ways of specifying the linearity of an amplifier. We have the 1 dB compression point, that is the point where the output of the amplifier departs 1 dB from the ideal response. So look at this. Here we have a 20 dB amplifier. If we have 5 dB on its input, it generates 25 dBs. If we have 6 dB on its input, it generates 26 dB. And this go on here. So we see that this 45-degree line here, dashed line, is an ideal amplifier. The true amplifier, the real amplifier, will depart from this ideal behavior as it saturates. We can see it here on the blue line. So this blue line here is the power in the fundamental tones. Is this power here of the fundamental tones. And when it departs 1 dB, we call this point 1 dB compression point. And this is actually very near to the maximum output we can get from an amplifier without too much distortion. If we try to operate the amplifier in this region here, after the 1 dB compression point, we gonna have a lot of distortion. If we try to back off, if we try to operate in this region here, we'll be very linear, but we're gonna decrease our efficiency, as you're gonna see. So the 1 dB compression point is very near to, is a very good figure to understand the maximum power we can take from an amplifier without too much distortion. As we saw in the simulation, as the amplifier starts to distort, the power starts to be shifted to the intermodulation terms. And we can see here the intermodulation terms, the power of the intermodulation terms, it increases faster than the output power. Why this happens? Because the intermodulation terms comes from the higher order terms in the polynomial, so they increase faster. This is very interesting. And if we extrapolate this curve here, guys, so if you look at this extrapolated line here, we see that for a mathematical amplifier exists a point where the third order product power will intercept the linear power, and this is called the output third order interception, because we are referring it to the output of the amplifier. And of course, this interception point is only a mathematical figure. It's very useful to understand nonlinear behavior of the amplifier, but this point will never happen because the amplifier will saturate first here. So as it saturates here, the third order products also saturate, and the saturation of the third order products happens from the fifth order products. As the fifth order products grow, the power is being shifted to the fifth order products, and these go and go and go, and the amplifier saturates, and the interception points are never reached, of course. But we can extrapolate this point, and it's a good figure of how well the PA behaves from the linearity perspective. And guys, if you want to learn more about power amplifier linearity, predistortion, and its use cases, you can click in the link in the description. Here on the Keysight Use Case website, we have a dedicated page about power amplifier linearity and digital predistortion. Keysight mastered linearity measurements, and they provide this very good application note about this that actually I use it as the reference for this video. To learn more about power amplifier Linearity, use the link in description and take a look on Keysight Use Cases. And here we see exactly that if we plot this transfer function here that we are using in the simulations in the dB scale here, so input power and output power in dB, we have exactly the figure that I drawed here. Okay, so we see that this figure here, this line here is real, and it can be directly generated by the transfer function, the voltage transfer function of the amplifier. So why we are not operating the amplifier in the very linear region? Because the efficiency will be lower. Remember, for very linear operation, we have class A. The maximum theoretical efficiency of a class A amplifier is 50%. From the practical perspective, it will behave with 30 to 35% of efficiency. Very, very low efficiency, even more for handheld devices. So as we approach saturation, we can create topologies of amplifiers like class B, class C, class A, class F. We can create different topologies of amplifiers where the active device behaves much more like a switch, working much more in the on and in the off state, and with more tricks to phase align the current and voltage waveforms to reduce the power dissipated on the active device. And all the efficiency gains we have with these different topologies and with these different tricks will make the operation much near the 1 dB compression point when the amplifier will start to distort but will deliver the higher efficiency. And of course, we have modulations that work better in saturation, like modulations that have only phase information, and we have modulations that have envelope information, that have information in its amplitude. If we have information in the amplitude of the signal, the nonlinear effect is a problem. So this is a trade-off. And here we see exactly this. If we have a modulation that only encodes the information in the phase, like a QPSK modulator that has 4 different output phases to encode 2 bits of information, each symbol here has 2 bits of information, we can use a high efficiency power amplifier that is working well into saturation, even with output powers over the 1 dB compression point, because the information is only encoded on the phase of the signal. But there is a catch here. It's not so simple, because we also have the effect of amplitude to phase modulation. And here I'm simplifying the problem a bit. We are talking on this presentation only about amplitude because it makes things easier to understand here, but we also have amplitude to phase conversion in the amplifier. So this can be a problem. It's not so simple, but it's a good approximation. It's a good mental model to think that modulations that use only phase information are very well protected from the nonlinear effect of the amplifier. And in the other side, modulations that are encoding the information using the amplitude also will have problems, like a QAM signal. And look at this. Look at a multi-tone modulation like OFDM. We can decompose a OFDM signal as a lot of parallel modulators that are summing the signal together before the amplifier. So take a look at this, guys. Imagine what's gonna happen if you think that each modulation signal here is a signal that will intermodulate with the others. So imagine this situation here, but with a lot of tones here, each tone modulated by its own signal source, and all these tones generating intermodulation with the others. This is the big problem for multi-tone modulations and modulations that encode the signal in the amplitude. Here we have a simulation showing the effects of passing a modulated signal through this transfer function here, or base nonlinear transfer function, and we see that the QPSK signal is amplified, but we don't see any significant effect on the data. But here for the QAM, we see that this clipping effect happens for the symbols that has higher power. So this clipping here that is happening when we approach the large signal behavior of the amplifier is indeed distorting the modulation, is corrupting the signal we are trying to transmit. And for this simulation, I'm simulating with a little back off. I'm simulating with little lower power than the 1 dB compression point. If we go deep into saturation, this would be much more distorted, would look like a circle. So imagine what would happen with even higher constellations, higher order constellations. All the symbols would be smashed together. And guys, we also have a problem that's not exactly a practical, but is more like a mathematical problem. That is, we always consider a transmission system as a linear process. We have linear mathematical tools. We use linear mathematical tools to design, to understand, to model the system. Filtering, modulation, encoding, all this stuff, bandwidth, symbols, all this stuff are linear concepts. And this is why we can subdivide it in blocks, and we can think about each block, we can mix blocks together, we can change the order of the blocks, and this works because we have a linear toolbox, mathematics, and also linear models in your mind. When we place a nonlinear component, a very nonlinear component like the amplifier, we break all these assumptions. Because think with me, probably it's possible to create modulation and demodulation techniques that would recover the signal that was very distorted by a nonlinearity. Probably in many cases, it's possible to create a black box, a magical black box that would decode a very corrupted signal by a nonlinear effect. But this is so hard to design, and we even cannot understand how this would work, because all the toolbox that we have, the mathematics, linear systems, all the analysis concepts that we have are linear based. This is a very interesting point of view. When we apply nonlinearities, we break a lot of assumptions, we break our knowledge about how things work, and we cannot deal even more with them. Very interesting. So what we could try to do to use more nonlinear amplifiers, more efficient amplifiers in conjunction with higher order modulations. How we can deal with the nonlinearities, how we can reduce a little the nonlinearities of the amplifier, so we can create products like a smartphone that needs to transmit very high data rates using a large bandwidth in conjunction with an efficient amplifier so the battery usage is low. Well, a technique that's used today in almost all telecommunication systems is predistortion. That's commonly called DPD, digital predistortion. And in this technique, we try to model the nonlinearity of the amplifier, and we use the DSP, the digital part of the system, to apply the nonlinear function in reverse, so we can counteract a little the effect of the amplifier. And here we are seeing the Saleh model. Saleh model is a very old model. I think it was one of the first models that were used even for traveling wave tube amplifiers. And this model is a nonlinear model that is controlled by 4 parameters, A and B and alpha and beta. And this model here models the AM to AM, amplitude to amplitude distortion, and also the amplitude to phase distortion of an amplifier. And we have here a simulation. So here I simulated these two formulas here, the Saleh model, and we see that indeed it simulates an amplitude distortion profile, it models an amplitude distortion profile, and it also models amplitude to phase distortion profile. As I told you, the amplifier also has amplitude to phase distortions, but we are ignoring it in this presentation. And what I did here, guys, is that I choose A and B that models the amplitude to amplitude distortion to try to model the nonlinear amplifier we are using for simulations. This one here. And we can see that they are not the same, of course, because this is an arbitrary nonlinear function that I programmed. I used here a hyperbolic tangent function, I think. I also add a term here that changes a little. You can see that the negative portion is different than the positive portion. This is an arbitrary transfer function, nonlinear transfer function. And here we have the Saleh model that has A and B, these two terms here. Let's see what terms I used here. We can see here that I used 1.25 and 2.8. This is A and B, and this is exaggerating here a point that I want to show you. The model is only a model. It will not be equal to the amplifier, never. This is a model of the amplifier It will help to correct the amplifier. It will help to understand the amplifier behavior, but it is not the amplifier. The real amplifier behavior happens to exist only in the real life, and the model tries to model it. So we can see that the Salem model has similarities, but it's not equal. And now that we have a model of the amplifier, we can create a predistortion system. We have data source encoding and modulation, and the modulation signal, here the output of the modulator, is applied to the inverse Salem model. In this example here, to the inverse of the PA, this will predistort the signal. So when the signal goes to the amplifier distorts again, and we counteract a little the effects of the distortion. And we can see it happen here. This is the output of the inverse model of the amplifier. So we are predistorting the constellation, and when we apply this predistorted constellation to the amplifier amplifies the signal. You can see that signal level here is higher, and we counteract the effect of the nonlinearity. But you can see that this is not perfect. We have a little bit of nonlinear effect, okay? It's much reduced from this case here. We have a very big improvement, but it's not perfect. And why we cannot use this digital technique, this digital magic, to make a perfect amplifier? Because we have the analog limitations. We have the physical limitations of the amplifier. Take a look at the curve of the amplifier, guys. As we enter here the large signal behavior of the amplifier, there is nothing we can do to increase the power here. Look, the output voltage becomes flat as the amplifier starts to clip. There's no magic here. We cannot increase even more, try to predistort, increasing a lot the input power, because the amplifier will be limited. So what predistortion can help us is to make able to operate the amplifier near the 1 dB compression point. So we still need to back off a little to work more in the linear region of the amplifier, but we can increase a little the power and use predistortion to operate in a region where the amplifier is more efficient. So predistortion is not exactly a way of fully linearizing the amplifier, but it's more like a technique that we can use to increase a little the efficiency of the overall transmission system. Well guys, if you liked this video, give a thumbs up and subscribe to the channel. Don't forget, take a look on the Keysight Use Cases page about Power Amplifier Linearity, link in the description. I see you in the next video of All Electronics.